Dr. Yakumeko, Dobrogoff, and Julius for helping me and being mentors through this process. It's been a fun journey, and glad to almost call this chapter concluded. So without further ado. So the question I'll start off with was, can modern control techniques provide engineering cost and schedule savings for DoD Navy autonomous systems? Specifically, I looked at fixed-wing aircraft because that was easy for me to work with out of Robo Dojo and things like that. So kind of diving deeper into that, I looked at the published DoD documentation for autonomy's roadmap, and they outline two key things: underutilized existing capabilities, and then also open technical challenges needing investment. And what I noticed was that guidance, navigation, and control is white in this case. So it's kind of a known product. We've been using guidance and navigation control for a while, and it's kind of a closed case. Well, I sort of hypothesized that maybe that's not the case. Modern control these days hasn't really been brought to the forefront and reattacked maybe some of these issues that could increase performance and ultimately reduce costs and time to first flights. So the SE method that I chose to use that fit this process was a waterfall method. Starting with that problem statement, kind of some key requirements popped out. The whole idea was, could I create a modern controller, a flight controller, that would minimize the engineering burden for controller tuning across agnostic fixed-wing aircraft platforms? What I mean by that is, regardless of what the aircraft looks like, the shape of it, manufacturing difficulties, inconsistencies, etc., is there a better, more contemporary flight controller that would account for some of these issues, instead of having engineers spend hours and hours and hours training these old conventional algorithms? The second was, the airframe is assumed to be unknown but time invariant. So aircraft, as we know, are not linear; they're very unlinear. But conventional control, like PID, is assuming that the aircraft is at a fixed airspeed and doesn't change that much, PID works. Well, the problem is aircraft are very nonlinear. So those controllers can be less robust than they might otherwise could be. But the big thing here was time invariant. So the aircraft isn't changing. An F-18 looks like an F-18. It doesn't magically turn into a C-130 in the middle of its flight, right? So that's sort of a gross statement there, because an F-18 does change in flight. It drops slats, it drops flaps. It could occur battle damage and things like that. So those are some of the thoughts that I was kind of rolling around in my mind, which brings me to this ultimate goal, which I wasn't sure if I was able to be able to achieve or not, but I was successful in actually achieving it. Was that the airframe is assumed to be unknown and time invariant, meaning that the airframe could change in flight, such as battle damage or lowering your flaps or servo hardovers, those kind of things. So this is the process I walked through. I looked at some conventional controls and ultimately ended up choosing one of them. Put it in simulation, software in the loop to test it on the actual autopilot in simulation using like X-Plane and things like that. Then I prototyped an aircraft, and I brought one to show you, like kind of the scale of an airframe that I was working on, so something about that size. It's about $4 of Dollar Tree foam board. It's really cheap and easy to manufacture. I could produce one in about a day, so it didn't really hinder my actual research, which was testing the algorithm. And then finally, what you're looking for is flight test and validation. If you can get to flight test and actually prove it in actual flight tests, your credibility goes up. So that was the ultimate goal. So fortunately for me, early on my time at NPS, I was fortunate enough to help in some of the flying of the NPS swarming aircraft. And what I quickly realized was that all these aircraft are made by the same manufacturer, right? So you can just tune one controller, use a conventional PID controller because the airspeed's not changing, and sort of make all these assumptions. Well, that's actually not true. The engineers that were on this project under Tim Chung very meticulously had to check center of gravity, aileron deflections, etc., because the tolerances, the build tolerances from the factory that made the 100 airframes just weren't adequate. And so, again, is there a flight controller that could be utilized to nominalize that behavior? And this is actually a quote from Randall Beard in 2006. So it's not a new problem. People have kind of known this problem is around. So the solution I chose on a cursory level was a modern control technique called adaptive control. And modern is is relative, right? So adaptive control started to see its roots in the early or late 50s. And specifically, it debuted itself primarily with the X-15 project. And that was quoted as being one of the most successful projects of NASA with over 200 sorties. However, towards the later stage of the development, because of the high dynamic pressure of the aircraft, the dynamic range of the aircraft, they wanted to move towards an adaptive control strategy to help mitigate some of those issues with the aircraft being non-time variant. What ultimately ended up happening was their understanding was very nascent and naive for robustness characteristics of these kinds of controllers. And so ultimately in 1963, the adaptive controller resulted in a complete departure of controlled flight, ultimately killing the pilot at about 63,000 feet. So from the 1970s to the 1980s, a lot of people kind of took a break from adaptive control because it's kind of scared aerodynamicists. So they took a step back and looked at the mathematics behind some of it to maybe prove the robustness of these strategies with mathematics. X-36 in 97, a tailless aircraft, used an adaptive controller with some success, and then the L1 adaptive control that I modeled my controller around was in 2006, had some test points that were also successful. That's kind of the background. So here's kind of an architecture of why you would when and where to use adaptive control. So if your process dynamics are constant, then you can just use a standard conventional PID control. However, if they're changing, i.e. your airspeed's changing, you're putting flaps down on the aircraft, then you need to do something different. So the conventional way it's done is with gain scheduling, because these variations are predictable. So when you drop a JDAM and the speed is increasing as it approaches the ground, those are all points that you can gain schedule in your conventional controller. The problem with that is it's very costly, which I'll discuss. And then lastly, adaptive control really shines when there's unpredictable variations, like battle damage or actuator hardovers and those kinds of things. So what I really wanted to do was push some of these benefits of adaptive control into these predictable variations as cost savings. So what you see is, again, this is like the JDAM scenario where you have one controller, no adaptation, it's pretty low cost and there's really low complexity. But when you actually apply it to like a JDAM, it has 500 gain scheduled separate controllers for each one of these airspeed scheduled points. Well, that results in a lot of wind tunnel testing and flight testing, which is extremely expensive, right? So the idea is, hey, could we use one controller that's an adaptive controller, arguably slightly more complex, but relatively the same cost? And what you see is that some of the newer or some of the older adaptive controllers, like model reference adaptive control, ended up actually being equally as expensive, because to tune them and get the noise characteristics from blowing up and increasing or decreasing your robustness, it required a lot of Monte Carlo simulation, and you're right back where you started, right? So it's still the same problem. You spend flight test money or wind tunnel money, or you spend Monte Carlo money. So from my perspective, what I wanted to do was maybe fix that problem. And then there's a controller called the L1 adaptive controller that offered some of those capabilities potentially. And the idea is that instead of having to do Monte Carlo simulation, you actually end up staying right here the whole time. So that's kind of an overview of what I did. How does it compare to a conventional PID controller? So typically you have some reference command coming into the controller. Then the plant represents like the airframe or the aircraft or the system you're trying to control. And then ultimately, the resultant state gets fed back to the controller and then closes the loop. So that's the conventional way that you might think about a controller for an airframe. And what does adaptive control look like? So you basically have some reference model that you want to idealize around. I want the F-18 to fly like this, regardless of my airspeed, regardless of battle damage, regardless of anything. That's the ideal model. Just give me that, please. So that's what's established in your reference model. And this adjustment mechanism ultimately looks at the state, just like the traditional feedback controller. It looks at the state of what's going on, feeds that to the adjustment mechanism, and says, hey, how am I performing with respect to this reference model? And then that then acts as a self-tuning regulator, sort of, to change the parameters of the controller to get you what you actually desired. So it's a smarter control mechanism. There are a lot of different types of adaptive control, so I did a quick analysis of alternatives to figure out which ultimately one I wanted to choose. So some of the contemporary stuff is neural networks, that's a big hot topic these days, machine learning, AI, etc. Recursive least squares approximation models. These are harder to prove robustness, and recursive least squares are also harder to guarantee that you converge to correct values, etc. But in the last case, this Lyapunov-based method is essentially measuring the energy of the system state and whether that energy is decreasing or increasing or decreasing. If the energy is decreasing in the system, you know you have robustness. So that's the foundation for the mathematical proofs of what you're underpinning your aerodynamics on. And it seemed to be a very promising method, so that's what I went with. So this is the actual architecture. One thing I'd like to point out is what the method, or what the actual reference model looks like, and I'll come back to that, as well as this filter. This filter, ultimately what it does is it's the novel piece to this new adaptive control technique, and it infers that the actuators on the aircraft are bandwidth limited. They can only move so fast. The airframe is bandwidth limited. So why are we trying to control the aircraft, or even model in your reference model frequencies that are faster than you can control? So if you can limit the control signal going into the plant with some bandwidth limitations, does that offer robustness? And as it turns out, this specific control, the L1 adaptive controller, and is ultimately why I ended up choosing it, is because it offers fast and robust adaptation. So with the Monte Carlo simulations, you kind of had to choose, like, do I want fast or do I want robust? And this specific controller decouples robustness from the speed of adaptation, which is pretty incredible. So starting from first principles, I took aerodynamic, basic fixed wing equations of motion, and then also the aerodynamic moments to reduce back into what the L1 adaptive control companion model was established through the mathematics. So one thing I wanted to point out here is that the fixed wing inertial tensor is non-symmetric, so there is inertial coupling. And then as well as in your moments, they're also coupled across axes. So in order to produce this, I make a very big assumption that there's no aerodynamic or inertial coupling. That's a pretty bold statement. It's obviously grossly incorrect, but as it turns out, the fast adaptation and robustness proved a very stable system, and it essentially acts as noise that is accounted for by the controller, and you can totally disregard it, which is an amazing find. So back to the biggest thing in this whole process was converting the mathematics to actual code. I found that to be very daunting, and it was probably one of the few things that was lacking in this research was connecting those dots to practical application, and that was what I spent most of my time on. Things like processor speed limits how fast you can adapt and things like that. But this controller specifically offered a really robust approach to actually implementing math equations into discrete code. So kind of the bread and butter of the results that I achieved. First thing I want to talk about is software in the loop going into flight test. So I used software in the loop simulator called X-Plane. It's a very common aircraft simulation. And what I found was, in the pitch control specifically, what I found was that for conventional control, you'll see there's this steady state offset. It never quite meets the demanded signal. But for the adaptive control, it was great. It was able to adapt. And one of the things that is happening here is when you pitch down, the airspeed increases. And like I was saying before, when the airspeed changes, your model changes. So the adaptive control is clearly winning in this case. This is the example I saw in simulation. So the elegance of the high fidelity simulator that I was using mapped perfectly in a flight test. So the section in green is under adaptive control, and the white is under PID. And what you see is the exact same thing, which was awesome. So under PID, there's some steady state error, and under adaptive control, there's no steady state error. And of course, in actual flight tests, you're going to have some increased noise as well. So sort of the same thing for flight test validation. This shows deploying the flaps on this aircraft right here. Under adaptive control, you see no real perturbation from the demanded signal. You really can't tell, that it's underperforming. However, under PID, when you lower the flaps, there's a sharp spike because the aerodynamics changing. and the increased moment due to the flaps lowering, and then also when you lower the flap, or when you raise the flaps back up. So you don't see these perturbations when you actually are under adaptive control, which is quite remarkable. Same kind of thing here. This was an off-trim case. The aircraft trim is unknown. How fast can you adapt? And the adaptive controller adapts way faster, which is awesome. So what the time constant here, what this shows me is that I was able to adapt within less than half a second. So for conclusions, the overall objective, to drastically reduce engineering effort required for T&E phase of autonomous fixed-wing aircraft. That wasn't really touched on my flight test results, right? Because it's very qualitative. You kind of have to take my word for it. This controller is extremely easy to tune. On the first flight, it was so apparently obvious to me. What would take me 2 or 3 flights to tune a PID controller for one axis, I tuned in less than 2 minutes. So that was obvious, and one of the things that I really wanted to point out was that was great that I was able to achieve that overall objective, but there were so many added benefits of using these modern control techniques, like what I found in the case of all of the flight testing with steady state error and adapting and all of those things, etc. So the ancillary benefits of this controller really make it a marked improvement over the conventional controller. So my overall thoughts and applications in the NPS swarming, you don't have to spend all that time, painstakingly checking the center of gravity and all these things, because you don't care. The controller is going to learn the aircraft within less than half a second anyways. And it learns it on the fly all the time, real time. So if anything changes, if you get hit by another aircraft, by like say another swarm or something, it doesn't matter. It'll still fix it as long as it's within the control bandwidth and capability of the airframe in that damaged state. Some other things like F-16 improvement to autopilot. F-16 autopilot struggles in asymmetric loading. So if you fire a missile off of one side and you have a missile on the other side, at high angles of attack, the flight controller, the pitch flight controller, rapidly departs control flight. It's a known thing. They tell the pilots, hey, just don't exceed these limits. But with a control like this, you don't care about these asymmetric cases, because the controller's adapt in real time anyways. So with that, I'll leave you with the 30 lines of code. The solution looks easier when you know the answer. But with that, I'll take any questions.
I dare you.
Hey Ryan, what was your flight profile that you flew when you were doing flight testing?
So basically it was just a square box, and the only reason that was the case was because I needed to keep it close to me. So what I would do is I just made a long rectangular pattern, and on the downwind leg, as soon as I turned downwind, I would run all my control sweeps, and then as soon as it would turn downwind or upwind, then I would stop.
So it was mainly control surface actuations.
Step responses and those kinds of things. So in the case of flap deployment, I would deploy the flaps and not touch anything else. So the flaps get deployed, flaps come down, and then I would just watch the pitch and pitch rate of the autopilot. And then what made the testing really fast in flight was on the transmitter. I had 2 switches that I could toggle for adaptive control on or off for pitch and then roll. And so on the upwind leg or downwind leg, and I would turn on the adaptive control. I would lower the flaps. I would raise the flaps, and then I would turn the adaptive control off, lower the flaps, raise the flaps, and I could get that all in one pass. And then I did that multiple times until I validated that, okay, yeah, it's a very repetitive process, and the tuning that I have is as good as the tuning that I can achieve. So that was kind of the process. One thing I noticed right away was that when you tune a PID controller, it's sort of arbitrary and you just have to take initial guess. If you get that initial guess wrong, the controller can just blow up. The plane will go completely unstable and almost like destroy itself. With this architecture, I never saw that. What you saw was a laggy control that was obviously underperforming. The control was just hunting. It was just way behind the aircraft, and it would just oscillate like real slow. On the flip side of that, when you increase the gain, you would see an oscillation, like a high frequency oscillation, but the aircraft would never depart controlled flight. It was always bounded, and that was one of the fundamental theories proposed by this control, is that the output and the air states were always bounded, and I saw that.
So the outer limits, what was the outer limits? Did you try anything bizarre, like put down the flaps on one side?
So on the fixed wing aircraft, not the flying wing, but the other aircraft, I started to test like asymmetric flap deployments. So I had 4 servos, one for each aileron and one for each flap. And so one of the failure modes I tested was, well, what if one of your flaps is stuck down? Unfortunately, I ran out of time for flight testing of that specific kind of buildup, but almost immediately what I found was, unfortunately, the asymmetric flap deployment, PID and adaptive control performed equally well because it just wasn't enough change in the aerodynamics of that specific case. Some of the other ones, like the steady state error that I found in pitch, was by accident. I was wanting to just prove the step response of PID versus adaptive control, and I kept noticing every time the PID, whenever you push the nose down, it would have steady state error on the negative side, but not on the positive side. And then I started doing some research into why that was the case, and found like, oh wow, it's not the case in adaptive control. It's significantly outperforming. So kind of the road ahead is this autopilot is limited by 400 hertz, and whenever you discretize anything mathematical, you want to make that loop frequency as fast as you possibly can. And 400 hertz is okay. I proved this algorithm runs at 50 hertz, but realistically, you want to be running in kilohertz or even higher. So the newer autopilots that are coming down the pipe should support that, but I proved the lower limit of 50 hertz, which is very low. This algorithm still works.
Okay, well, thank you very much.